Assalamualaikum and hi. How are you today? Okay. Um, for today's lecture, we'll continue with the learning Unit 11 that will be discussed on the topic of implicit derivatives, partial derivative, and its application. Still remember, we have discussed on the some of the basic rules of the derivative in LU9 and also its application in LU10. So the objectives of this lecture is to find derivatives by using implicit or partial differentiation, to find slopes of tangent by using implicit differentiation, to find partial derivatives of functions of two or more variables, to evaluate partial derivatives of functions of two or more variables at given points, to use partial derivatives to find slopes of tangents to surfaces, and the last one is to find and evaluate second and higher order partial derivatives of functions of two variables. So we start with the implicit differentiation discussion. As we can see, y equal to fx can be solved or can be defined by using explicit functions of x that will give us in the form of dy over dx or equal to f prime x. For example, here let's say we have y minus x squared equal to 0. Then y is equal to x squared. And then when we differentiate this dy over dx is equal to 2x. Okay. Then, however, not all equations involving x and y can be written in form of y equal to fx. In some cases, the derivative of dy over dx at a point on the graph of, for let's say, y squared equal to x will require us to determine which of these function applies before taking the derivatives. Therefore, in this case, we can use the implicit differentiation as a solution. Okay, when y is an impact functions of x, we find that dy over dx by differentiating both sides of the equation with respect to x and then algebraically solving for dy over dx. Okay, let's discuss on the first example of implicit differentiation. Okay, use implicit differentiation to find dy over dx for y squared equal to x. Then find the slopes of the tangents to the graph of y squared equal to x at the points 4, 2 and 4, negative 2. So we can derive both sides of this equation with respect of x. Therefore, we found that it will be equal to d over dx of y squared equal to d over dx of x. Because in this case y is an implied, therefore, or implicit, then y squared is equal to 0, y squared is equal to x can be represent by u here. Therefore, instead of using y square, then we have ux square. Okay, then is equal to x. Okay, then to derive this, we can use the chain rule. So based on the chain rule, we have d over dx for y square equal to d over dx of x. And the differentiations of this y square will give us 2y, but we have to multiply it with the dy over dx. Okay, dy over dx. That is the derivative of the dx over dy over dx for y square. Okay, then the differentiations of x is equal to 1. Therefore, in this case, we have to solve this algebraically so that at the end of the solution, we found that it is equal to dy over dx only without any other value beside it. Okay, so we have here transform this into dy over dx equation. Therefore, we have dy over dx is equal to 1 over 2y. Okay, then to find the slope of the tangents at the points 4, 2 and 4, negative 2, then we use the coordinates of the point to evaluate dy over dx at this point. Therefore, figure 11.8 shows the graph of y square x with tangent lines drawn at the 4, 2 and 4, -2. Okay, then as we noted previously, y squared equal to x, so will give us the two function that is y equal to square root x, that is also equal to x power 1 over 2. And at the same time, y will be equal to negative square root x or equal to negative x power 1 over 2. So when we illustrate this graph, then we found that figure 11.9a shows that this is a graph for the functions of y equal to square root x, and 11.9b is actually the functions of y equal negative square root x curve. Okay, the solutions of y squared equal to x can be also represented as the y equal to square root x or y equal to negative square root x. Y equal to square root x is actually same as the y equal to x power half. Same also for the y equal to negative square root x. So y is equal to negative x square power square. Okay. Therefore, when we differentiate this dy over dx, then we found that it is equal to 1 over 2x power negative 1 over 2. Therefore, we have dy over dx is equal to 1 over 2 square root x. Okay, as shown as this. Okay, then the second one, we also found that when y is equal to negative x, square root x, therefore, okay, dy over dx is equal to negative, sorry, y is equal to negative x power 1 over 2. Therefore, dy over dx is equal to negative 1 over 2 x power negative 1 over 2, or it is also equal to negative 1 over 2 square root x here. Okay. Then therefore, the slope of the tangent cannot be found at x equal to 4 unless if y coordinate can be identified. Okay, and it shows two different ways of solving the function with same results, but in some situation explicit derivative for y is difficult or impossible. Therefore, the solution for this is by using the implicit derivative. Okay, then let's discuss on this example. Find the slope of the tangent to the graph of x squared plus y squared minus 9 equal to 0 at square root 5 equal to 2. Okay, therefore, in this case, we have taken the derivative for both sides. Therefore, we have the differentiation of x squared, differentiation of y squared, and the constant that is negative 9 and also 0. Therefore, the differentiations of x squared is actually the explicit derivative. Therefore, we have dy over dx is equal to 2x power 1. Okay, then plus with, because we are having the derivative of y squared here, therefore this is equal to 2y, and then multiply by dy over dx. Okay, so this is the implicit derivative. Then we plus 0 for the derivative of negative 9 and 0. Therefore, from here we transform this back by using the algebraic technique, and therefore we have 2y dy over dx is equal to negative 2. Therefore, dy over dx is equal to negative 2 over 2. Okay, negative 2 over 2. Then based on that, then we found that it is equal to negative 2x over 2y. Okay, therefore we have negative 2x over 2y, it is equal to negative x squared, x over y. Okay, then the slope of the tangent to the curve at this point evaluating dy over dx is equal to negative x y at it's the value of the derivative as okay, so this slope of the tangent to the curve at this point, okay, is the value of the derivative at this the value of the derivative, then evaluating dy over dx equal to negative x power 5, okay, negative x over 5 at 5 square root 5 2 will give the slope of the tangent as the negative square root 5 2. Okay, then now we move to the second parts of the derivative that is known as the partial derivatives. So in partial derivative, we have first order derivative, means that we are doing the first partial derivative for the function. So if let's say we have z equal to f of xy, this means that there are two terms that will be included in the function. Therefore, the partial derivative of z with respect to x can be denoted as the dz over dx by treating that the variable y is constant and taking derivative z equal to f of xy with respect to x. And at the same time, if we do the derivative of z with respect to y, then we assume that, or we're holding that the variable x is constant, and we're taking derivative of z equal to f of xy with respect to y, then we denote it as dz over dy. The notations of the partial derivative can be also shown by those notations. As you can see, if we derive the z function with respect of x, then we can rewrite it as the dz over dx, df over dx, or d over dx of f of xy, or fx of xy, or fx only, or dzx only. Same also for y. Okay, if we derive this partial derivative of z equal to fx with respect to y, then you see that the notation usually will be written as the dz over dy, df over dy, d over dy of f of xy and fy of xy, fy, and also zy. Okay, how do we do the the partial derivative? Okay, let's say we have z equal to 4x squared plus 5x squared and then y squared. Okay, then plus 6y cubed and then minus 7. Then the question asks us to find for dz over dx and dz over dy. Therefore, for dz over dx, we have to look at the terms that having x. That is only 4x squared, 5x squared, and 5x squared, y squared. So in this case, 6y cubed or 7 is known as the constant. Therefore, when we derive it, it is automatically equal to 0. Okay. And then in the case of dz over dx, and then we have to derive for x squared. So this is having an explicit derivative, therefore we have 8x. And then plus 5x squared y squared, means that we are differentiating this based on the x. Therefore we have 10x. And then y is remainder y as a y squared. Okay, then for dz over dy means that we differentiate at the function that is having y. Therefore, the function that is having y is only this and this. Therefore, we differentiate in terms of 5x squared y squared. So we have 10x squared y. Okay, 10x squared y. But then after that, zy cubed is 18y squared. Okay, then in the partial derivative, it has a graph that is surfaced out in the 3 dimension, that is representing the x null, y null, and z null. Okay, Therefore, the partial derivative with respect to x of such a function may be thought of as the slope of the tangent, that to the surface at a point x, y, z on the surface in the positive directions of the x-axis. Means that it's moving toward the x-axis instead of the y. Okay. Therefore, if a plane parallel to the xz plane cuts the surface passing through this point, and then the line in the plane that is tangent to the surface will have a slope equal to dz over dx evaluated at the point. This dz over dx can representing as this, that is dz over dx is x null y null, representing the slope of the tangent to the surface at x null y null z null in the positive directions of the x-axis. And similarly, in the case of the derivative of this z with respect of y, then we can denote it as this or this. And this partial derivative of dz over dy shows that we are having the slope of tangent to the surface at x null, y null, z null that is in a positive direction, okay, of the y-axis, as you can see by this blue line. Okay. Then another example. Let z equal to 4x cubed minus 4 exponential power x plus 4y square, and let p be the point 0 to 12. Find the slope of the tangent to the z at the point p in the positive directions of a, the x-axis, and b, the y-axis. So in this case, 0 is actually representing x null, 2 is representing y null, and then 12 is representing z null. Okay. Then in this case, okay, the question asks us to find for the slope of z at p in the positive x direction is given by dz over dx evaluated by p. Okay, the clue here is a positive x direction, means that we differentiate it with respect of z. Okay, then based on the question, it says that the equation of z is given by 4x cubed and then minus 4 exponential power x and then plus 4y square. And then 4y square. Okay. Therefore, in order to find for dz over dx, then we focusing on deriving the terms that having x, that is at 4x cubed and 4e power x. That is why when we derive, the derivative of 4x cubed is 12x squared, then the derivative of negative 4 exponential power x is negative 4 exponential power x. And then this can be denoted as the zz over the x, that is from at the point of 0 and 2. Therefore, we can substitute the value of x by 0 here, then found that this is equal to negative 4. Okay, this result negative 4 can be interpreted as that z decreases approximately 4 units for an increase of 1 unit in x at this point. Okay, y decreases because the value is negative, and then we have to always remember that because we are talking about the derivatives, although it doesn't shows that that doesn't ask us to find for the marginal, but the derivative itself is actually mentioning that or presenting that this function will be changed due to the 1 unit increase in x at the point. Same also if we want to find for the slope of z at p in a positive y direction. Okay, therefore we differentiate this equation by y. Okay, by y, then we found that we only have 4y square here. Therefore, when we differentiate, this is equal to 8y. And then the partial derivative can be denoted as the dz over dy of 0 and 2. Therefore, we can substitute y equal to 2 into the equations that we found just now for the dz over dy. Then we found that it is equal to 16. Then this 16 means that at the point of p, that is 0, 2, and 12, the function increases approximately 16 units in the z value of 4 and a unit increase in y. Okay, then the next part is the partial derivative can be derived again, and this is known as the higher order partial derivative. If z is equal to fxy, then the partial derivative functions zx and zy are called first partials. Then these partials of zx and zy can be also derived, and in order to have the second partials. Therefore, z equal to f of xy has four second partial derivative. Let's say we have zxx. Zxx means that we are derive the first derivative of z with respect of x, then we derive again with respect of x. Therefore, this zxs can representing as d to z over dx square, or it is also same as d over dx times dz over dx. Therefore, we are actually having both derivative taken with respect to x. Then the second one, let's say we differentiate y with respect of zy, then we can denote this as d to z over dy square. Therefore, we have d over dy multiplied by dz over dy. Then both the derivative taken with respect to y. Then we have zxy. What does it mean by zxy? Zxy means that we already do the first derivative of z with respect of x. Then after that, we derive again for the second derivative with respect of y. Therefore, this can represent as the d to z over dy dx, or d over dy times dz over dx. Then first derivative taken with respect to x, second with respect to y. Then we have also zyx, means that we are doing the first derivative for z with respect of y. Then the second derivative, we derive this with respect of z. Therefore, this can be written as the d to z over dx dy, or d over dx times dz over dy. So this means that the first derivative taken with respect of y, then after that with respect of z, x. Okay, let's at this example that is on the second partial derivatives. If z is equal to x cubed y minus 3xy squared plus 4, find each of the second partial derivatives of the functions. Okay. In this case, we have to find for the first partial derivative that is based on the zx and also zy. Because we want to find for the zy, then we have to look at the function who has the x here. So we have we can derive with respect of x for the first term and also the second term. Therefore, based on this, the derivative of zx is equal to 3x squared y and y, where y is remain the same. Then the derivative of negative 3xy squared is equal to negative 3y squared. Meanwhile, for the first derivative of z with respect of y, then we derive also in terms of the first term and the second term. Therefore, we have x cubed then minus 6xy. Then in order to find for the zxx, then we have to look at the first derivative of zx. Then we derive it again with respect of x. Therefore, d over dx for 3x squared y minus 3y squared. Because of 3y squared, there is no x, then automatically this is equal to 0. Therefore, we have 6xy. Then zxy means that we have to look at the derivative of z with respect of x. Then we derive it again based on y. Therefore, we derive at the both term, that is 3x squared minus y, and then minus 3y squared, and it is equal to 3x squared minus 6y for the second derivative. Then zyy means that we have to look at the zy as the first derivative. Then again, we derive it with respect of y. Therefore, d over dy for x cubed minus xy is equal to negative 6x. Then for zyx, we have to look at the first derivative of y. and then derive it again based on the x. Therefore, d over dx for x cubed minus 6xy is equal to 3x squared minus 6y. And then based on the partial derivative, sometimes when you see some of the equation will give the results that zxy is and zyx are giving the same results. Therefore, this will always occur if the derivatives of the function are continuous. Therefore, if the second partial derivative zxy and zyx of the function z equal to f of xy are continuous at a point, then they are equal there. Okay.